So I think actually you can kind of think of this as a research forum talk that got a little bit lost. I want to talk to you today about some work that mostly has been done by one of my students, Yi Huang, but we've also been working with Anako Lakina from Guavas and another professor, Jim Zhu. The subject of this work is basically this. We want to basically figure out ways to help you folks detect and locate network disruptions inside your own networks quickly. Now you may already be thinking you have ways to do this, and that's actually part of the reason I'm here. I'm going to end actually with a bunch of questions. I'm here actually to learn a little bit more from you about how these types of things are done and how well your current techniques work today. But I'll talk to you a little bit about the approach that we've taken to solving this problem. Another reason I'm here is to get more real data to help us improve our techniques, because the results of our algorithms that I'm going to show you today were based on the Abilene backbone network, because that data is readily available. Of course, it would be nice to try this, the types of techniques we're developing in other networks and scenarios as well. So we're definitely interested in working with you to improve these techniques. As I mentioned, you're probably already thinking, well, I know how to find disruptions already. I have, there are many ways to do this with SNMP traps, syslogs, netcool, etc. What we're looking at here is, can we apply some new types of complementary techniques and looking at complementary data sets to perhaps help you deal better with the massive amounts of data and noise that some of these tools and techniques are known to generate. So basically noise reduction is one of the first goals. The other is fast detection. So to some extent, some of the tools out there may already do this as well, and that's actually something I'm here to learn a bit more about from you folks. So those are the two main issues we're trying to get at with looking at these new types of techniques. And I'm going to tell you in a minute just what's particularly new and interesting, I think, about the techniques that we're looking at in more detail. But the key idea basically is that we're looking at network-wide correlation and analysis of network events. So rather than looking at single router outputs or graph by graph what's going on at single network devices, what we're doing is basically on the fly building models of what's going on across many different routers in the network and looking for correlated blips across those and saying, well, if a lot of things are if things are happening in a lot of different places at once, that may indicate something that's interesting. So I'll get to that in just a minute. As I mentioned, this is just a first step. We are looking at complementary data sources, to the existing things you're probably already looking at, like SNMP and so forth. We think that there's probably other places to look that may help in the goals that I talked about right at the beginning, that is in terms of noise reduction. As I mentioned, this is just a first step. We're looking at BGP routing data inside the AS. In particular, we're looking at routing changes experienced by all the routers in the backbone. So we're currently looking, extending some of these techniques by looking at things like IGP data as well. But it's certainly possible that we should be looking at other data sources as well. So when I end with some of the questions, that's where I'm looking for some input. So in a nutshell, what we're doing is looking at the BGP routing data as collected at BGP monitors in the Abilene backbone for every router in the backbone. So what those monitors are giving us, since they're iBGP monitors, are routing changes experienced by each one of these routers. So the traditional approach, and what you might do if you were sort of looking at through one of your traditional eyeglasses would be to take one of these graphs. These are routing updates per 1 minute bin for the routers in the backbone over the course of quite some time. There are a few problems here to notice, or a few things that I want to draw some attention to, and some of you are well aware of this. One is, of course, that there's always noise going on, right? You can't say, well, when some routing change happens, that has to be interesting, right? There's constant churn. The other thing to notice, I think, is so it's a little bit hard to see, but you can certainly see on the slides posted to the web, to the NANOG website, that I've circled a few examples of places where links have failed in the network, or something interesting has happened. And one thing to note is that it's not always the case that interesting events correspond with lots and lots of routing updates, particularly at any single router, right? And the converse is also true. Just because a big spike of updates happens doesn't necessarily mean anything interesting just happens. So this gets back to the kind of original problem, which is, yeah, there's lots and lots of data to look at. How do we make sense of it and reduce the level of noise so that alarms aren't going off every minute? The key approach we're looking at here, and I think the thing to take away in general, aside from just looking at BGP data, because there are other sources that we could certainly look at, is that if you're just looking at a single stream of routing updates or a single stream of data from any one router, there's often limited semantics, particularly if you're looking at routing. What we're getting at here is moving beyond just simple reporting of routing routing messages that may indicate a problem, and really mining them across the network to say extract some meaning. For example, we think based on what's happening that a particular link may have failed, or some type of interesting event may be occurring. So rather than looking at any single stream, we're developing these techniques that basically look across the network at all of the streams in parallel. And well, why are we doing that? Because in fact there are dependencies in these data streams. So why not exploit the dependencies that exist in these data streams and look at them all together? Rather than treating each one of these streams of data independently, as we know, big network events actually may cause some types of correlated blips, right? So for example, as I've shown in these pictures, right, if you've got a link failure either internally or perhaps on a peering session to a neighboring AS, you're going to very likely see lots of routers change what they're doing, or the routes that they've chosen at a particular time, and you may see all those changes happen right at once, right? So that's the techniques that we've developed are basically geared towards catching those types of events, right? Lots of routers doing something, doesn't have to be big, but if they're doing it all at once, we'll get it. This, I think, is really kind of a natural way of looking at network data, because the network does have structure, right? Just looking at a single routing stream gives you some information, or a single data stream of any kind gives you some information. But there are dependencies in the network, right? The topology, the configuration, and so forth. And the analysis that you do on the data should be somewhat cognizant of the dependencies that exist in the topology that you have. So that's basically what we're trying to model and use to do some more intelligent analysis than sort of simple reporting based on single data streams. So the system that we've built basically has two pieces corresponding to the two aspects of diagnosis. The first is detection, right? So you want to know something interesting just happened. The key there, of course, is reducing the amount of noise so that when you get these detection alarms, it's highly likely that something interesting actually did happen. So that's where we're using this network-wide analysis of BGP routing updates. And again, I do want to, when I end with questions, I want to emphasize we are interested in in the process of looking at other types of data streams as well. It just it was one of those incidents of, the drunk guy under the lamppost looking for his keys. But so that's the first step, is looking at the network-wide analysis for possible disruption events. Then, of course, the second step is identification, right? So we want to know, now you've got a bag full of events that may be interesting, and you want to know what just happened, right? Did a peering session go down? Did a link or a node fail? And for that, we basically use some model that we've built of the network in terms of, what IP addresses are where, in terms of routers within the network, IP addresses on peering sessions, and so forth. And we use that information plus the information that's in the routing updates to say, okay, we think you've got a node failure here or a link failure at this point, so forth. I'll talk about each of those in sequence. So I'll first talk about detection. How do we figure out something interesting is going to happen, or just happen, I'm sorry. I'm not going to get into the mechanics. Basically, what we're doing here is principal component analysis, which is glorified SVD. And if you're interested in the technical details, there is a paper, and there's a link on the last slide to the paper, which will be at Sigmetrics. But the main idea behind the approach is to start without any model of what dependencies exist, right? You just take all the streams of routing data, and then you build a model of what looks normal, what trends look common, and based on those, your model of what the common trends look like, you look for deviations from those trends. And the techniques that we've developed are very good at extracting deviations where lots of routers experience some kind of change altogether that looks unusual. So we developed this technique and evaluated on the Abilene network. Another nice thing we had with the Abilene network, where if we were to work with you on problems like these, it would be nice to have, was some documented list of disruptions that we actually knew occurred. So they document publicly, you can go grab it yourself, all the link, node, and peering link failures, and not only their existence and type, but their location and duration. So that helped us do some validation as well. Using the techniques we developed, we were able to catch everything that was documented on the list in terms of internal disruptions, nodes and links going up and down. Definitely room for improvement in terms of failures on peering sessions, but we still got most of those. I say acceptable false positive rate because it's hard to tell, for example, if we detected something and it's not documented on their list of known failures, whether or not they just didn't happen to know about it, or whether or not it in fact is a false positive. So again, that would be a place where we could certainly improve our techniques by talking with people who are running networks who actually have some knowledge of what in fact may or may not have happened, rather than just doing black box post facto validation. They have some reporting techniques, I think, again, that are semi-automated. You might note here that it does take a fair amount of time, in some cases, for these guys to actually detect and locate the source of these disruptions. As we're developing the system that actually implements the algorithms, we hope to do a little bit better than these. But again, your mileage may be a little different, and we're definitely interested to know about that. The second piece, after detecting that something interesting happened, is identification, right? What just happened and where? And there we have pretty much some simple heuristics. We take the bag of interesting events, and we look, again, network-wide for certain types of features in the BGP routing update streams. For example, to take the first case there, we can look at the set of updates, count the number of IBGP, count the number of global next hops that we see in the BGP routing updates in the total set of next hops. If that number decreased, then it's very likely that a node has failed, right? If no other router in the network is picking a particular node as its egress, then it's likely that node is no longer there. If not, then something else happened, and we have similar types of heuristics by looking at sets of these next hop addresses in the BGP routing updates to figure out exactly what's going on. I'm going to skip this. I'm going to skip through it quickly. This shows basically what we detected in terms of events where nodes and links go unstable. The smaller circle that's on the right side are the set of reported events on the Abilene mailing list, and the circle on the left are the set of events detected over a 6-month period using the method that we developed. You might note that yes, though the overlap between is reasonable, the size of the set that we detect that doesn't overlap with the email list is still also rather large. You'll note that it's still not perhaps prohibitively high. That's something like 2 or 3 alarms per day, perhaps. But this again goes back to the point where we had some limitations as far as knowing exactly what was truly a false positive. Some of those 535 may be false positives and probably are, but without actually knowing what was a real interesting event, it's quite possible that many of those actually were something interesting as well. We did happen to look at those and note that it did appear that link and node disruptions were occurring in many of those cases, but without sort of ground truth documentation of them, it's hard to say for sure. So coming to the summary of some of the things we found, I mean, you might sort of wonder first off the bat, why are we looking in BGP? Could you even see most of this stuff in BGP? Well, it turns out most of the stuff is there in some form. If you look at the documented disruptions, most of them show up in the IBGP monitors in some form. Many of them are very low volume. So that graph I showed at the beginning, where I circled some things where there wasn't a whole lot of BGP noise, a lot of the disruptions are of that form. So a simple approach of setting a threshold on a single routing stream is likely to give you a lot of noise or miss many of the interesting events, or both. Setting such a threshold would be pretty hard because the size of the update spikes, if you will, generated by any particular disruption can vary by many orders of magnitude. Again, why look at the network-wide analysis of these streams? Well, most of these disruptions involve some BGP noise at more than 2 routers. So that kind of makes sense, like for the reasons I described before, the intuition I gave. But it also sort of argues, well, why not make use of that somehow in the analysis, right? If we know that it's there, if the correlation is there, we should be designing and developing algorithms to extract that correlation if it's a good indicator of the disruptions. BGP routing data works pretty well. Other people have tried using BGP update data for this problem in the past. We think it works certainly at least as well as any of those techniques. But again, it's arguable that we should be looking at other data, and I'm open to suggestion there. I definitely would like to know what you think. Some numbers for you, and I wanted to end with some questions, actually. If you don't have time to, or the desire to step up to the microphone, please send me email with some thoughts on any of these. I'm very interested to hear how we can take this in future directions and make this approach more useful. In particular, I know that there are many tools out there that people use that leverage, say, SNMP or syslog data, et cetera. How happy are you with those approaches? Are they too noisy? Are they too hard to configure, too manual? What types of network faults are you most interested in catching and occur most frequently? Where's the pain point, essentially? How effective are these existing tools in terms of, reducing the noise level? Do you have to go in and manually tweak things to get the noise level down to an acceptable level? Is it still too high? Are they telling you meaningful things about where the failures are and how to fix them? Things I'd really like to know. What about incorporating other types of data? So I'm fully aware of SNMP and syslog and those types of things, but what do folks think about incorporating other types of measurements like active probes of the network for use in fast detection, for example? Everything we've looked at here is passive, but perhaps a combination of approaches may result in less noise or faster detection. Most importantly, I think we're looking to improve our techniques. This is just the beginning. So you can have a look at the tech report there, which will be revised and appear later this year at Sigmetrics. But in the meanwhile, we are definitely interested in making this useful. So interested to hear your thoughts. Thanks.
Are there any questions for Nick? It doesn't look like it. One thing I would add, Nick, is on that slide is degree of fault, right? Mm-hmm. So SNMP is fine for letting us know that a T1's down. It doesn't help you when a peer across 6 different peers decides to announce 30,000 more routes to you, mm-hmm. Mm-hmm. Right? So there's applications there where this is helpful. Okay. So, cool. Okay. All right.
Oh,
no more
maybe
questions?
We've got one.
No, I think he's just going back to his seat. All right. Thank you very much. Bill, we're ready for you.